people, welcome to this episode. This video is going to be a continuation of where we left off, which is the PyTorch dataset and data loaders. And the reason why I had to show you dataset and data loaders before this video is because we need to understand the concept of dataset and data loaders to also understand what I'm going to teach you today. And so today's video is going to focus on how to use the high-level APIs of PyTorch to implement neural networks. And for an example, we are going to re-implement the linear regression model that we built by hand. And if you remember, this linear regression model was simply learning how to convert temperature values from Celsius to degree Fahrenheit. And so what we're going to do with the PyTorch NN API is to re-implement this using the high-level APIs, and then we will see how simple it is to build models that way. Okay, so let's get started. As always, I'm going to start by importing the modules that we need, and this time you're going to see something new which is called torch.nn as nn. So I'm importing the neural networks module or the neural networks interface of PyTorch, and I'm aliasing it as nn, similar to how we alias numpy as np. And I'm going to import torch.nn.functional as f. And what this functional module or functional API does is to provide us with a lot of helper functions and utility functions, like there are a lot of definitions for the different loss functions that we use in neural networks. And so as opposed to the low-level API where we had to manually define the mean squared error, with the nn.functional interface, we already have the mean squared error defined for us. So the more you reuse, the lesser errors you can make in your implementation. And so the low-level APIs are still there for you to use anytime you have to do something custom. Okay, and so we also have the torch.optim as optim. And this also gives us a set of already made optimizers. And optimizers are responsible for handling the core of the gradient descent algorithm, which we implemented here. So in this implementation, we're not going to see this lines of code over here because the optimization classes that we have from the optim API makes it easier. And lastly, we're going to import numpy as np. And so now I think we are set with all the imports. Let's go ahead and then recreate the data set that we've been using all along. So features is equal to torch.from numpy, and I'm going to do exactly what we did. So a range, and we're going to generate from -50 to 50, and we want to specify the data type to be equal to np.float 32. Okay, I spelled float wrongly. Okay, now let's create our output. So our output is also going to be just our features multiplied by 9 divided by 5.0, and then we add 32 to it. So the idea is we have to be able to build a model that will end up telling us that the bias is 9 divided by 5 and our weight should be something close to 32. Okay, so now we have a data set. As always, let's go ahead and then print the shape. So we do output the shape. Great, so we have 100 samples to learn from, and that is enough for a simple problem like simple linear regression. Let's go ahead and then create our data set. So I'm going to say data set is equal to torch.utils.data.tensor dataset. And this is the point where you find yourself wanting if you've not already watched the previous video. So don't skip it so that your learning experience will be much smoother. Okay, so we have the data set. I'm going to create a data loader. I'm actually just going to call it loader or something. Yeah. Is equal to torch.utils.data.data-loader, and I'm going to pass in the data set that has been created up here, and I'm going to pass in a batch size For this simple example, I'm still going to retain a batch size of 1, but in subsequent videos, when we start doing image classification and multivariate regression, then we will set the batch size to something bigger than 1, but for now 1 is okay. Alright, so now we have our data set and data loader created for us, and this is where the difference begins to show up. So you can see that in the manual implementation of linear regression, we had to manually create a tensor to represent our weight and also a tensor to represent our bias. And some of the things we had to make sure to do right was to make sure that the data type was flow32, because that is what PyTorch deals with. And I mean, you can go to flow64 and flow16, but that is they are exceptions. And then we also had to make sure that we set requires grad to true. Otherwise, we cannot calculate the derivative of the loss with respect to M and B. Now, the good news with the torch.nn API is there is a class called Linear, and you just specify the input data dimension and the output data dimension. And out of this information is able to figure out the shape of your weight and the bias, and it's going to initialize it for us. For example, let's say model is equal to nn.Linear. Okay, so the linear takes in features, that is an integer, and output, that is also an integer, and you can also specify whether you want to include a bias or not. By default, that is true. So let's say our data set had 3 items in it, and it was going to predict 1. So let's say we are building a model where you feed in information that has 3 components. You feed in a row that has 3 columns, feature sets that has 3 items in it. And the idea is to have the model predict 1 output. If we do this, let's see what happens. We can print model.weight. And let's also print model.bias. Model.bias. So you can see that automatically this linear class knows that because there will be 3 data points coming into this neural network or node. I mean, you can have multiple linear modules. I mean, we'll get there, but for now, what you need to understand is that this nn.Linear is stating that there is a linear, there is a network which is going to do linear transformation, and by linear transformation I mean this multiplication here. So we have to manually make sure that we multiply the weight by the input data, and we added the bias to it. Now we also don't have to implement this because it has already been implemented in the linear class for us. Okay. As a matter of fact, why don't we see what the linear class does? And I've shown you that trick already. So we do linear, and let's see what it does. And so it says blah blah blah. You can read. It says it applies a linear transformation to the incoming data, and the math is y hat is equal to x times a transpose plus b. This formula you have seen it several times. So instead of writing this code, the linear class already implemented for us, and all we have to do is to tell it how many items or how many features are in our data that will come into, and how many output do we expect. Now we just want 1, so 3 and then 1. It means the data that you feed into this network has 3 items, and you expect this network to produce just 1 item at the end. When I say item, I mean a number, because you know that linear neural networks deals with numbers all the time. Okay, so we run this, and if you took notice, you can see that anytime I create an instance of linear, the weight changes because the weight and the bias are initialized randomly for us. So you can see that anytime I run it, they get new. So this is the weight values that our network is going to get started with, and then we will have to use gradient descent to reduce or increase it up until the point where our network is able to solve the problem for which it is being defined. Okay, now another thing you can do is you can print a list. So the linear module has a function called parameters, which gives you a list of an iterable of all the weight and biases. Basically, these are the tensors that has required grad set to true automatically. So if I do model dot parameters, then you cast it to a list, you can see that it basically contains the same thing, but over here we got the weight separately and then we got the bias separately. But if we build a much larger neural network which has more layers, then the model.parameters is going to show us all the weight and biases in each of the layers. And by the way, let me just show you what I mean by layers, neural networks. Okay, so let's choose any of the images here. Now, whenever you search for a neural network, you are sure to see something like this. What it means is these are what we call the layers. So this is layer 1, layer 2, layer 3. Okay, and so in the example that we have here, when I said nn.Linear 3 and then 1, what I basically mean is that the data is going to go through 3 nodes and is going to return just 1 at the output. Okay. All right, so if you wanted to use nn.Linear to build this layer here, what you're going to do is you say nn.Linear, and you can see that the input is 1, 2, 3, 4. So 4, and then the output is going to be 1, 2, 3, 4, 5. And it continues that way. Okay, so I believe you understand. I don't want to over-explain things. All right, great. So now let's create this model to fit our problem. Our problem is such that each item in our features, which is also the Celsius, the value of a temperature in Celsius, is just 1, and our output is also 1. It's not like we combine multiple things and we get a single thing out. So what we do is 1 goes in, 1 comes out. Let's run this, and now you can see that the model has its weight set to 0.2255 and its bias set to negative 0.6821. Of course, when you run it again, it's going to change because it is initialized randomly. And when we do models or parameters, you can also see that we have the parameters over here. So what have we done here that is different from what we did initially? So initially, we had to manually create the weight and the bias, and we had to initialize it ourselves, and we also had to implement this linear transformation formula over here. In this case, we do not have to do it, and mind you, this is all we've done. All these I am just using to show you what's going on internally in the linear module. Okay, all right, so great, we have our model created. How do we go about training the model? The way we go about it is, first of all, let's take a look at what we did previously. So first of all, we had to make a prediction on our data by doing this linear transformation, and then out of that we will calculate the loss, which we call MSE, and we also had to define MSE on our own. So we calculate the loss, and now we had to do the back propagation where we call loss.backward, so that the derivatives of the weight and bias, the derivative of the loss with respect to the weight and bias will be calculated and stored in their corresponding grad attributes. And then over here we have to say with torch.NoGrad, and then we have to manually set calculate the updates that we need to make to our weight and bias. And we also had not to forget to zero out the gradients for our weight and bias, because PyTorch accumulates the gradient, so you have to always remember to zero it out. Now the good news is that with the NN package, we don't have to do some of these things. We can skip a lot of these things. Okay, so now we have our model, and we want to go ahead with the training. One thing I want you to know before we continue is that the model is callable. So the model can be called with a tensor, and it's going to do the linear transformation calculation for us. So let's just say P is equal to model, and I'm going to feed in just some fake tensor. So I'm going to say torch.tensor, let's say 1.5. Okay, let's see what happens. So I'm going to print P here. So basically, I fed in 1.5 to our model, and our model produced 1.03 to 0.3438, blah, 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 negative number. Okay, fine. So this is how you feed in data to the model. And so this is how you make prediction with a model, okay? So like the steps we saw in the low-level implementation of linear regression, we are going to replicate that over here. So let's first of all get our loss function. And luckily enough, we don't have to define the MSE here. Yes, you can do that, but it is already defined for us in the torch.nn.functional interface. And so what we do is, I'm going to say our loss function is equal to f.msc loss. Okay, so it has been defined as MSC loss in the functional API. And so we can assign that to a value, and then we can call that. The next thing we want to do is we want to create an optimizer. So you say optimizer is equal to optim dot. There are a lot of optimizers there. We're going to start with SGD, which stands for Stochastic Gradient Descent. And look at what it's saying about itself. It implements stochastic gradient descent, optionally with momentum. We are not going to deal with momentum now. But so this is an optimizer class that has been created to know how to optimize a set of tensors that have required grad set to true. And you can see that whenever we list our model parameters, you can see that the weight and the bias have required grad set to true. And so the optimizer is a class which we can pass a list of tensors that have requires grad set to true, and the optimizer will automatically know how to run gradient descent on them. Everything will come in and it will make sense to you before the end of this video. So I'm going to pass in model.parameters. So the model.parameters is going to give you all the tensors in your model that requires grad is equal to true. Basically the parameters of your neural network, okay? And the next thing we can do is we can set a learning rate. Let's set it to 0.0001. So e minus 4. So 1 times 10 to the power negative 4. You want a small learning rate. You can feel free to change it to whatever you want. Okay. Now let's set our epochs, which is the number of epochs we want to train for. Let's see how many epochs we have to train here. So we trained for 7,000 epochs. Wow, that's quite a lot. Let's start with just 100, and we can always increase it. Okay, now what was the next thing we did? In fact, as a matter of fact, I can copy code from here, okay? So for now, I'm not going to keep track of the losses because I don't want to plot them. We will know if the network is working. Okay, so we loop over the number of epochs, and what we want to do now, we are going to use the data loader, okay? So for now, we'll say for input and target in loader. So now for each epoch, let me put this here to explain something. So for each epoch, we are going to iterate over this loader, and this loader is going to return items in our data set, and the data set is made up of our features and our output. The features is the temperature values in Celsius, and the output is the temperature values in Fahrenheit. So the data loader is going to loop over and return these one by one because we set batch size to 1. If we set it to something else, then it's going to return them in batches of whatever we set it to. Okay, so now we have our inputs and our targets. What we do is we do a prediction with the model by feeding in the inputs. Okay, so whatever input we got from the data loader, we feed it into the model so the model can come up with its own prediction. Okay, and then once the prediction has been done, we can go ahead and evaluate the loss. Okay, we can go ahead and evaluate the loss. So what's going to happen here? We say loss is equal to, we call loss fn, and then we pass in our predictions, and then we pass in our targets. Okay, now we have the loss. So what do we do? This is similar to, let me compare it to what we had here. So over here we had to do loss is equal to self.mse blah blah. So it's almost the same. Okay, fine. So we call the loss fn. Mind you, I said it's almost the same, but now we didn't have to define a lot of things. We didn't have to define the mean squared error ourselves. Okay, now the next thing we do is to do loss.backward. And this is where the derivative of the loss with respect to all the parameters that are included in the optimizer will be evaluated. Okay, mind you, when you call loss.backward, loss knows that the weight and bias were involved in the calculation, because in the model, that is where the weight and bias are defined, and the loss is obtained by calculating the difference, the mean of the square difference between the predictions. And so all the calculation that goes into model are also recorded on the gradient table. So when you do loss of backward, the derivatives for all the parameters are also evaluated and stored in each parameters .grad attribute, which is what we used here. But as you will see soon, we are not going to use these lines of codes anymore. Okay, so now the back propagation has been, the derivatives have been evaluated. The next thing we do is to call optimizer.step. Now this optimizer.step call here, which is just one line of code, replaces everything here. So 1, 2, 3, 4, 5. So with just optimizer.step, we are replacing these 5 codes. And remember that in the manual implementation, we would have gotten our linear regressor wrong, and it wouldn't work properly if we forgot to zero out the gradients for the respective parameters. And so over here, we also have to do the same. When you call optimizer.step, what actually happens is that it is going to do this gradient descent update. Okay, all right. So the next thing is we call optimizer.zeroGrad. And what this one is going to do is going to zero out all the gradients for the respective parameters in the list of parameters that was passed to it. Okay, and then the next thing we want to do is we want to check if the number of epoch is equal to something, then we can print out certain things. I mean, it's not compulsory, it's not part of the training process, but it's good that you get feedback. So let's see what we did over here. You can see that over here we were checking if the number of epochs is equal to 100, then we print blah blah blah. We can do a similar thing over here. So what I'm going to do here is I'll say if epochs mod 100, so we want to get updates on every 100th iteration. Then we print. So basically I'm going to print epoch, let's say E over epoch, so I can see, let's say epoch 1 of 100, epoch 2 of 100, blah blah blah, epochs, and then I'm going to print the loss, which is also equal to loss.item. Okay, then what do we do? Now I think we have a good enough training loop to run. So let's go ahead and run it and see. So something is wrong, and I know what is wrong. I'm using F strings and I forgot to bring the F. Okay, so I'm going to run. I mean, I'm going to start from where I defined the model. The reason I'm doing that is at this point the model has been trained already, and retraining it will not make any change. So I'm going to start from here again, run this. All these are not paths, but I had to use them to explain things to you. Okay, so now we get here. Let's see what's going on. So one way you get to know if your implementation is working is that your loss has to be reducing. Still, there is something wrong. So we see the epochs always starting from 100. Ah, I see why. It's because of where we place the if statement. We have to go to after the for loop. Okay, now let's rerun this. Let's see what's going on here. Still something wrong. How do I fix this? So we have our loss, we have the optimizer, we loop over, we do this, then we check in if epoch is equal to this. Ah, okay, I see why. Because we are doing just 100 epochs and I'm giving updates only on the 100th epoch. So let's do 10 and I'm going to start the training again. Okay, 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 let's go. Now let's train. Right, so now you can see that our gradient descent implementation is working, and the way you get to see that it has to be reducing. Of course, there are times when it will be jumping up and then it will still come down, but what you need to notice here is it has to be reducing. And how do we know if we have had enough epochs or iterations so that we can trust this model? The way we can do that is we want our weight to be similar to 9 divided by 5, which is 1.8, and our bias should be close to 32. So let's see what we have in there. To do that, we can just do print a list of model dot parameters. Okay, and let's see what we have in there. So you can see that our weight is 1.7, which is not quite close enough. I mean 1.8, we can round it off, but our bias is 27, which is far away. So what it means is we can increase the number of epochs that we train for. And then let's start the training afresh. So I go here, run this, run this, run that. And so let's wait for the 200 epochs to finish, and you can see that now we have a much smaller loss. And so we can see that indeed we have 1.79, which is almost 1.8, and then 31 point this, which is almost 32, but we can still do better. And so this is where the art of training comes in. There is no science to this. You just have to keep playing with it until you think your model is smart enough and you can stop training. Okay, so now we are training for 300 epochs and done. So let's see what we get now. So yes, we can stop here because our weight is supposed to be 1.8. We have 1.8002, which is fine, and our bias is supposed to be 32. We have 31.9265, which is also fine. So the question is, how do we make a prediction using this model? The first thing you want to do is you can set the model to evaluation mode. When you set it to evaluation mode, it will stop tracking the calculations, okay? Because it's a waste of computing resources. If you are training, you want to track the calculations, but if you are using a model, you don't want to track because you are not going to calculate derivatives. The derivatives are needed to come by the appropriate weight that the network needs. Once you find that, you do not have to keep track of your calculations again. So to do that, you do model.eval. So if you call model.eval, you set it to evaluation mode. And then what we're going to do is we can pass in some tensor for it to evaluate. So let's say predict. Let's predict for torch.tensor. So let's try to convert 100 degrees Celsius. Okay, and then let's print what we get in Fahrenheit. So let's print the prediction and let's see what we get. Object of type long but God scalar blah blah blah, and this is true because it is expecting a float and by default it assumed the long. Okay, let's play with something. Let's set this to 0.0 and let's see if it's going to take it. Yeah, so it infers the data type by the value that you put in there. Otherwise, you should be specific by saying d type is equal to torch dot float 32, and this should also work. So at this point we have been able to convert 100 degrees Celsius to Fahrenheit, and let's see how we can do that. So 100 Celsius to Fahrenheit, and let's see what we get. So that is 212, and what does our model give us? 211.9. So if you round it off, it's actually 212. And so you can see that aside all the cells I included to explain things properly to you, actually using the high level APIs of PyTorch makes your work and your life easier, and it is more intuitive when you are reading this code. So basically we started off, I'm just making a recap here, then we end. So we started off by initializing a model from nn.Linear. You specify the input dimension and the output dimension. These were just introspective stuff. We were looking into what is going on in the model. And once you come here, you need to have a loss function that you are going to use. And the loss function comes from the torch.nn.functional interface, which we have aliased as F. And it's pretty much a convention within the PyTorch community. And then we initialize an optimizer, which is SGD, and we pass in the model parameters, which is what we investigated up here, so you know what they represent. And we set a learning rate, and then we set an epochs to 300, and the normal training loop begins. So what you do is you use the loader to get your data in batches, and then you feed in the data into the model. You calculate the loss the backward, you call optimizer.step and optimizer.zeroGrad, and you can do some feedback, printing what's going on in your training phase, so that you can see if your loss is reducing, and indeed it is so. And now we have a model that is on par with what we did with the low level API. So thank you very much for watching. Don't forget to subscribe, and I'll see you in the next video.